welcome to class of Satellite and Radar System. This is Unit 3, Part 2, and we are talking about Direct Broadcast TV, that is DBS-TV. So this is the lecture in continuation to the previous lecture, where we have gone through the brief introduction of what DBS-TV is and how it has started. What is its role in today's entertainment industry and how satellite is fulfilling those needs. So these are the contents of my topic today. We are going to cover C-band, K-underband home satellite TV, digital DBS-TV, the detailed description of DBS-TV receiver, and error control in digital DBS-TV. So whenever we talk about the role of satellite in today's life, entertainment is one of the field where satellite serves us in a way that makes our day-to-day life easier, and maximum revenue is earned through entertainment industry where satellite plays an important role, right? So if we talk about satellite TV, it's an old concept, right? From there we move to cable TV, DTH, and now DBS. In cable TVs, we used to have coaxial cable that used to give us the input information, which was received from with the help of an receiving earth station, which directly communicates to satellite. But further, it is distributed to home using some coaxial cable, that is wired connection. Whereas in case of DTH, direct to home services, each user is provided with an antenna. This is a kind of parabolic antenna which is placed in a rooftop that receives signal directly. So that's why this service is called as direct to home, and DBS-TV is a successor of it. A little more advancement in the field of picture and video technology, more incorporation of digital signal processing makes us a better entertainment thing for us, right? So if it and the bands that helps us in communication for DBS-TV, that is our C band, which is our 6 and 4 gigahertz, that is 6 gigahertz for uplink frequency and 4 gigahertz for downlink frequency, and K underband, right? We operate in approximately 12 gigahertz here, right? If we talk about early 1980s, the development of low noise gallium arsenide field effect transistors, amplifiers for C-band, and improved threshold extension demodulators for video signal receivers. These allowed much smaller diameter antennas to be used to receive C-band FM video signals. Those are distributed through geo satellites. So what do we focus here? That use of field effect transistors, that is, these are fast switches, helps us achieve smaller size of antenna, right? These provide faster switching and they are of better technology, so we can move towards smaller dimension antenna, right? And what kind of satellites are used for our TV communication? That is our DBS-TV, that is our geostationary satellites, which are placed at approximately 36,000 kilometers, that is 35,786 kilometers altitude, that is at a height, this much height from Earth's surface. And they do have their own, there are conditions for geostationary satellite. Their period of revolution around Earth is equal to the period of rotation of Earth, that is 1 sidereal day, which is approximately 23 hours and 56 minutes and 4 seconds, right? And that lies with the equatorial plane, that is angle of inclination is 0 for here, and that orbit is an exceptional orbit which is circular in shape, not elliptical in shape. So the satellites placed in geostationary orbit that helps us in DBS-TV reception, right? DBS-TV originally started in Europe and the United States in 1980s using analog FM transmission in KU band. In 1990s, digital video transmission became feasible and several systems were developed by the United States in 12.2 to 12.7 gigahertz. In this Ku band, we perform most of our communication. Right? This is a band specifically allotted to DBS-TV services. The development of low-cost Ku band antennas and receivers and high-speed digital integrated circuits specifically for DBS television that incorporate QPSK demodulation. So what it incorporates, what are the technology that is included here that makes it a better choice is QPSK demodulation, error control, decryption, that is security is incorporated, and MPEG decoding made DBS TV practical, right? These are some salient features of it. The DSP, digital signal processing, is incorporated in a single integrated circuit that implements the digital video standard used by all the DBS TV systems, right? So DSP plays an important role here that makes the video quality and picture quality better for us. So let's talk about DBS TV receiver. We know it has basic 4 parts, that is the dish antenna, the set-top box, the cable connection, and the remote that we have. So let's see what this complete receiver is composed of. So for any communication system which is ongoing in radio frequency range, the first element of the receiver is an antenna. So that antenna must be capable of receiving that particular frequency. Here we are working in Ku band, and the band which is specific for DBS TV is 12.2 to 12.7 gigahertz. So we must be having an antenna that is capable of receiving such frequency, RF antenna, right? So this is the parabolic antenna. At our rooftop, we do have it in dimension which is approximately 0.5 meter diameter, right? This is the feed of the antenna, right? All the signals falling here, they are gathered and collected by the feed, which goes through wired cable to our set-top box, right? What happens here? Let's consider it a simple receiver. What does a communication receiver has, how it works in case of RF communication? The first part after the antenna is low noise amplifier, LNA, right? The role of low noise amplifier is to reject the noise and to amplify the low power signal. As the signal has traveled quite a long distance, we know having the satellite at 36,000 kilometers above the Earth's surface, such a long distance, and it is coming back to it's coming back again to Earth. So it is roundabout. It is covering quite a large, quite far distance, right? So LNA will solve me the purpose. It will reject out the noise, and it will amplify my low power signals. Next is my bandpass filter, right? The role of bandpass filter is important in any kind of receiver. So a good receiver will have n number of combination of amplifiers and bandpass filter. We can put n number of amplifiers and bandpass filters, right? So this bandpass filter will help me select out the initial signal frequency, right? Next, it goes to a mixer, which could be called as a product modulator as well. This is the symbol for it. This is the universal symbol which we use for product modulator. It requires 2 inputs. So one of the input is the RF frequency that we receive. Another input to it will be through a local oscillator. Why do we call it local oscillator? Because it generates a carrier wave which is, which is in our hand. We can manipulate it, we can control it. So in case of coherent detection, if we study communication in detail, in case of coherent detection, this oscillator must be generating the wave which is coherent in phase and frequency to the carrier wave which was used at transmitter for modulation, right? So here, as the receiver and transmitter are geographically far, but still we are having the information of that phase and frequency, and we are generating it locally. That's why this oscillator is called as local oscillator. Here, the frequency which we generate depends on what kind of receiver it is. If the frequency next like if I am this is A and this is B, I can have multiple combinations here, right? A plus B, A minus B, A into B, A multiplied by B, A square B, and so many, right? And by using a suitable filter, I can extract out the frequency which is desired, right? So here, what I do, I choose the IF frequency, which is the intermediate frequency, right? So what I do basically is, after receiving the radio frequency, I do not directly down convert it to the baseband signal. I first down convert it to IF frequency, that is intermediate frequency range. That is, I do not directly jump from gigahertz to hertz. There is an intermediate range which could be, megahertz or kilohertz. So that is my intermediate frequency range, right? So it is down converted to IF range, and for that IF frequency, I use another bandpass filter and another set of amplifier, right? Now, here I can see the same arrangement lying here as well. So what I'm using is, I'm using this in double conversion mode, right? So I'm using the double arrangement of it. So using double arrangement of it will help me acquire better signals, right? Accurate signals, to reject out more of the noise and to reach the power level which is desired, and to extract out the exact signal which we look for, right? So always a double conversion arrangement is better than a single conversion arrangement, right? Then it goes again to IF amplifier. Again we have bandpass filter. You can see that this gigahertz frequency is converted into megahertz frequency. Here the difference of these two will go 12.2 and 11.3. The difference lies in the range 900 to 1400 megahertz, right? So this is the IF frequency which is fixed for my DBS-TV, right? This again goes to the second arrangement, where it is again amplified, then it is passed through a bandpass filter, and again mixer or product modulator. Here the frequency which is generated by this can be controlled. Now this can be controlled to reduce error to much larger extent, right? So then it again here the IF amplifier. Now this frequency again reduces to some smaller value. Here it is approximately 70 megahertz IF amplifier, right? Then it goes to this amplifier again. Then after signal extraction, demodulation has to be applied, because any signal which has traveled a long distance must have been modulated at transmitter. So as this is the receiver, I have to perform demodulation, demultiplication, right? Usually the signal transmitted was a QPSK signal, so I'll be using a QPSK demodulator here. So QPSK demodulator, after this, the signal is again amplified, right? And then for signal correction and for security purposes, compression, decompression, security, all these things are applied through inner decoder, de-interleaver, because initially coding has occurred at transmitter, interleaving has occurred at transmitter, so we perform the reverse of it. Then we have outer decoder. Then after demodulation, we perform demultiplexing. And this is for video signal, MPEG-2 decoder. And finally, digital to analog conversion. That is, we need to see the video, right? Pictures in moving form. We need to hear the audio. These are analog signals. As signal has traveled in digital form, finally it has to be converted back into analog form from the digital bits, right? So finally we have a D2A converter, and we are able to see here the video and audio of it. That is analog output to TV set, which we get to see on our screen. So this is how my DBS-TV receiver works. All this has been explained in the theory here. The entire front end of the receiver is located at the signal feed in the form of LNB to minimize loss of signal. True. Loss of signal, and hence to maintain the lowest possible system noise temperature, which is true. The electronic polarizer is switched by changing the voltage supply to the LNB via the cable that interconnects the antenna and the set-top receiver. The entire 12.2 to 12.7 GHz band is down converted by the LNB to this. Here it is, my IF frequency, already discussed, where cable losses are much lower at KU band, right? This is a universal truth. The down converter consists of a dielectric resonator, local oscillator, and a mixer, true, which we have seen. A resonator, a mixer, a local oscillator, right? Followed by an IF amplifier and bandpass filter, already discussed. The high gain LNB can drive 100 meter of coaxial cable without any reduction in signal quality, where longer cable runs are needed. Amplifiers for this band and can be used to boost the signal strength, true. The set-top box accepts the entire 500 MHz band and separates out the individual transponder frequencies. Any one of these frequencies can be selected on demand by the user. So we get to select it, right? The user enters a desired channel number into the set-top box using an IR remote control. What we use remote control that works on the basis of infrared frequencies, right? For example, if there is we do have 362 channels which is stored in the lookup table, and by pressing the number we actually select that channel, that frequency from that lookup table. The signal from required transponder is then selected by the receiver, and by setting the correct polarization at the antenna, which is tuned, the set-top local oscillator to the appropriate IF frequency channel, right? So with the help of that lookup table, we decide which channel we want to, and by pressing that channel, we choose that particular frequency. QPSK signal demodulated, true, because at modulation QPSK was used. Here the bit rate is maintained at 40 Mbps. The bit stream is encrypted. This is a secure data and contains error control, coding bits and data bits. Bit stream is processed to correct and detect errors. De-interleaved and decrypted, all discussed, right? Finally, the digital demultiplexer extracts the bit for the wanted channel 362 here in this example, right? And finally, digital to analog conversion, which we have discussed, right? The lookup table here contains all the instruction regarding your demultiplexing frequencies and polarization. Next thing is how error control takes place in my digital DBS-TV. So for error control, it uses Reed-Solomon encoder and interleaver, a convolution encoder, right? So at transmitter, these all things are carried out, and when it is communicated at receiver, the reverse of all these things occurs in a way. Like first this is reversed, then this is reversed, and finally this. So we do have initially the convolution decoder, then de-interleaver, and finally the Reed-Solomon decoder. So we get output data here. So how it works, let's go through it. In my digital DBS-TV, transmissions typically use a transmitted symbol rate of 20 megasymbols per second, not megabits, megasymbols, using QPSK, which gives a bit rate of 40 Mbps. This is bits, symbol, right? The compressed digital video signal bit stream is first split into blocks of bits, and then this is encoded with Reed-Solomon linear block code. This is a kind of block codes have their own advantage in case of encryption. That is a separate field though. But for now, we must be knowing that block codes are preferred, as here, instead of encrypting bit by bit, we choose a block of like 8 bits or 16 bit or 64 bit at once to be encrypted. So block codes are always preferred. The coded bit stream is then interleaved and encoded again with a convolution code. So this convolution, these coding can be studied separately if anyone is interested, right? So at receiver, these bits are recovered and decoded. Now, if we talk about the transmitter of DBS-TV, we have gone through the receiver in detail. Now let's give a look to the transmitter as well. If we talk about the master control station and uplink, what happens here? Before transmitting the signal, what all things, what all technology that is used, and what all modifications we do to our signal, right? First, we are going to use a QPSK modulator. So first modulation occurs, right? Here, for modulation, we need the actual message signal and the carrier. So carrier is generated here with the help of this oscillator, right? So from here, and how do I get that signal? Let's come to this. How do I get that signal? Analog signal it was, audio and video. So first that has to be converted into digital form. So we use an ADC here, that is analog to digital converter, right? This is the first block. Then for video we use MPEG technology, right? This can be studied in detail, right? After this we perform multiplexing first, that is we enable so many channels to so many message signals to travel via a single channel, right? That is sent to the coder. This is for compression and security. Then interleaving, coding, outer coding, interleaving and inner coding. These are all for security and compression techniques, right? We use Reed-Solomon encoder, interleaver and convolution encoder here. And this data now again is QPSK modulated, then it is amplified as it has to travel long distance, then this is up converted. Frequency is converted as in uplink. Like if I talk about C band, it's 6 gigahertz and 4 for downlink. And like in KU band, we have gone through the band here. In this range, communication occurs, right? So up conversion, then low power amplifier, high power amplifier has its role in amplifying the signal. And finally, after multiplexing, we transmit that signal through earth station to satellite, right? So one uplink antenna will typically transmit up to 16 RF channels. So 16 RF channels can be transmitted at once. Each RF signal is a QPSK modulated KU band carrier with a symbol rate of approximately 20 megasymbols per second. It occupies a bandwidth up to 27 megahertz. The encoded, compressed, multiplexed and modulated signal is transmitted. And the modulation technique which is most famous in case of satellite communication is QPSK, right? 70 megahertz signal is up converted through a, usually we prefer bent pipe transponders, right? Here the HPA is usually rated at much higher power than normal operating output power level, right? Here the signals from any number of HPAs are multiplexed together in microwave combiners, so that the areas which are geographically far, they can be communicated at once. So let's conclude with the summary. We know that geostationary satellites are used for DBS-TV, and they have its role since 1960s. Right? Growth of cable TV, that is CATV, in United States started around 1970s. Right? The transponders on geosatellites can send video signals. They are capable of sending video signals, right, throughout the continent. Satellites are very effective way to distribute wideband signals, so they are used for broadcasting. C-band and Ku band are preferred here. Right? C-band and Ku bands are preferred here. A large fraction of all transponders in most of the world's domestic and regional geosatellites, they serve in television or entertainment industry, as we earn most of the revenue through it. Video distribution and direct broadcast television (DBS) have become a major source of revenue for the satellite communication industry. That's it for today, and these are the references which I have used. Thank you.